Hello everyone again. My name is Neoklis. I am the ESR3, and my research in the framework of OptiMACS project is manufacturing simulation. Today, I'm going to present you my work so far in the field of process-induced distortions of thermal composites with application in the aerospace industry. This research is conducted along with University of Nottingham, of course, Premium Marotech, and Airbus Defence and Space. Before going into detail, I would like to give you the big picture. So nowadays in the manufacturing industry, there is the goal to achieve a right first time approach. This means that we need to reduce manufacturing costs, delays related to manufacturing issues, and last but not least, increase product quality. These are the three main objectives that we are looking forward to achieve. Furthermore, there is an ongoing effort in the industry to replace the expensive INVAR tools that are used nowadays to produce flying parts with aluminum ones. Moreover, we need to reduce manufacturing times, especially for future projects. Parts that were used to be manufactured out of thermoset composite materials are now considered to be manufactured out of thermoplastic ones. And finally, we are always looking forward to reduce assembly times and costs with the easier assembly of components and structures. In order to achieve the right first-time approach, it's very important to know the shape of the part that is going to be manufactured. As you probably know, when we manufacture a composite part, residual stresses are induced to the part from its manufacturing process. And in order to achieve the right first-time approach, it's very important to know or be able to predict these residual stresses. Shape distortions are actually the combined effect of spring-in and warpage. Spring-in is defined as the reduction of an angle of a typical L-shaped part, whereas warpage is the bending or twist of a flat laminate. Here in this slide, you can see two structures that have suffered from spring-in and warpage. There are many factors reported in the literature that affect residual stresses and shape distortions. Svanberg, in his PhD thesis a couple of years ago, tried to evaluate and separate those factors into four main categories. So the factors that that have a large effect on shape distortions, like the cure seconds, the laminate of the part, and cure temperature, whereas on the other hand, factors like fiber content or mold material surface have small effect on shape distortions. To those factors, I would like to add stress relaxation, as stresses relax over time because of the nature of the resin, which is a viscoelastic material, and part shape and cure cycle. The majority of the residual stresses are generated during cool down from the final hole temperature. At this point, the material can be simulated as thermoelastic and Hooke's law can be applied. However, stresses built up earlier in the manufacturing cycle, we need to employ the viscoelastic material model in order to calculate them. In order to address this effect of process-induced distortions, the aerospace industry employs the so-called mold geometry compensation strategy. In this approach, the shape of the mold is different from the part that is going to be manufactured out of it. In order to be able to design the mold, we need to have an estimation or the knowledge from experience the residual stresses that are imposed to the part and create the distortions. Having these distortions, the expected distortions, we can then mirror them and create the surface of our mold. Here in this slide, you can see what is done currently in the industry to design a new mold for a new composite part. So every time we start from a nominal geometry. This is our target. The second step is to perform a kind of finite element analysis by employing a material model. And based on the results of this finite element analysis, we get distortions and we mirror them. And this is our first, let's say, surface for the new mold. Then we perform another finite element analysis to validate, to be sure and verify that the final part will lie inside the tolerance range that we have set for this part. If this is the case, we proceed to manufacturing. Otherwise, we keep on looping until this condition is met. In my research, I focused on a test frame which was provided by Primo. This frame is the TRL3 frame that you saw yesterday. It's not a flying part, however, it has many common features with flying parts. I modeled the frame with the use of solid elements and assumed orthotropic material behavior for each ply. The use of 3 integration points at each thickness direction. And I implemented my material models with the use of the OptiMACS UMAT subroutine. So regarding boundary conditions, in order to reduce calculation time, we start our simulation just before the gelation point. So we heat up until 108 degrees, where we hold this temperature, and then we cool down. We cool down until room temperature, where we demold our part, and then we trim it. Regarding mechanical boundary conditions, we keep all the transactional nodes, degrees of freedom of all nodes to 0, and at the demolding step, we release them, and we just keep fixed 3 nodes which are used to suppress rigid body motion of the frame. When I refer trimming, I mean that the number at the final step of the simulation, a number of elements are subtracted from the mesh in order to simulate the trimming operations that usually take place in an industrial environment. In this slide, you can see how UMAT subroutine communicates with a bulk solver. So the UMAT subroutine takes as input at every time increment the strain increment along variables which are in the memory. The job of the UMAT subroutine is to update the stress tensor and the Jacobian, and of course calculate the state variables which are used for the next time increment. When this is done, Bacchus checks if the principle of virtual work is satisfied. If this is the case, we proceed to the next increment, otherwise we keep on looping. In my research, I examined 2 material models. The first one is the well-known CHILE model, which stands for Cure Hardening Instantaneous Linear Elastic Model. This is a material model used widely in the industry and also in the academia. Mainly because due to its simplicity and its relatively good predictions. However, it cannot account for stress relaxation, which occurred during the manufacturing of the part. In the next few slides, I'm going to present you the software architecture that I developed to implement this material model. So the first step is to calculate the degree of cure at the current time step. When this is done, we can then calculate the glass transition temperature, the resin chemical contraction, and then we can calculate the resin coefficient of thermal expansion, the resin cure shrinkage, and by employing the CHILE formulations, the resin instantaneous E-modules. Then we can calculate the resin instantaneous Poisson coefficient, the thermal expansion strains, instantaneous fiber volume fraction. And when these all values are calculated, we can proceed to the homogenization step and calculate ply expansion coefficients and the homogenized properties of the ply, namely the E-module, G-module. Then we are able to calculate ply strain, the constitutive update our stress tensor and Jacobian, and give it back to the Bacchus solver. Here you can see the results of the simulation by using the CHILE model. And just to give you an idea how big this frame is, it's about 1.7 meters in length 175 millimeters width and a height of 100 millimeters. And this is actually half of a real flying part. Normally, a flying part has double this size. The next material model that I investigated is a linear viscoelastic material model, which was proposed by Harrison Poon a couple of years ago. Here you can see its mathematical formulation. The important thing here is to notice this variable here, d, which actually is the fictitious creep traces, which are subtracted from the elastic ones to calculate the stress tensor at every time increment. And this is the consistent tangent operator proposed by Harrison Poon. The viscoelastic behavior of the resin was modeled with the use of Maxwell elements. In the next slides, you can see the software architecture again that I developed. The difference to the previous one is that now, since we work with viscoelastic material models, we need to calculate seed factors, and this was done with the use of the VLF formulation. And then we are able to calculate the resin instantaneous in modulus with the use of Prompt series, and also by reading from the memory the Maxwell elements relaxation times and modulus. And everything is the same until the calculation of ply strengths, where we have this loop here in order to calculate the creep traces. And then we feed all this information to our constitutive equation and update the stress tensor and Jovian. And we exit our UMAT subroutine. Here you can see the results of this simulation. Two things are important here. First, that this material model compared to the CHILE one needs about twice the computational time, so it's more expensive. And as it was expected, because of the large amount of state variables that need to be calculated and stored at every time increment. And secondly, that it predicts larger distortions compared to the CHILE solution. However, with the use of viscoelastic material model, we are able to take into account effects that the CHILE model cannot, like cool down rates, cure time, and stress relaxation, which are time-dependent factors that affect shape distortions. Here is a direct comparison between the predictions of the two material models. As a basis, the CHILE prediction is used, and red color means outward displacement to reach the viscoelastic result, whereas blue, inward displacement. In this slide, I used experimental data which was provided to me by Primo. So what they did is actually they scanned the frame. They created an STL file, and I used this file to compare my results. I placed 14 points at specific locations in the frame and measured the deviation of the simulation results to the actual produced part. In order to do so, I performed a global best fit over the whole geometry in order to bring the two databases one on top of the other. And in this table here, you can see the results with green color. It's depicted which model is close to the experimental result. In the next slide, I have performed the same job. However, here the difference is that I performed a local best fit to the outer flange and web, since the outer flange is the one which is attached to the skin to the aircraft, and usually in the industry they have more strict tolerances there compared to the inner flange. And again, you can see the results. To conclude, the differences of the two material models tested are small. The linear viscoelastic model proposed by Harrison Poon predicts slightly better the experimental results. However, the CHILE model runs much faster, and I think it's a good value for money approach. And in order to increase the accuracy of viscoelastic of process-reduced simulations, the viscoelastic material models are proposed. However, for this specific model, we need to further validate it with other geometries to make a safe conclusion. Thank you very much for your attention, and I'm looking forward to your questions.
So thank you, Neoklis. And please, if you have a question, you can ask Neoklis now.